Okay, so now that we've covered the four main types of light sources or light emitters and their shapes and how to calculate and work with them, the last things we need to talk about are a couple. I want to have a couple extra details that I want you to know about that will enhance your lighting effects. And then I want to talk about how we can actually take these formulas and these theories, right, and integrate them into your rasterizers so they actually work. So those will be the last things that we talk about. First thing I want to talk about here is the idea of light attenuation, okay, otherwise known as fall off. So if you have, for instance, a candle in a dark room, then not every single surface of the walls around it is going to be completely brightly lit. That candle is only giving off so much energy, right, in the form of those photons. And so even though they may, it's not like they stop traveling, the photons, until they are absorbed maybe by different mediums. But I don't know why I have a half moon candle there. Oh, I can't draw today. There we go. So you have a candle in a dark room and it's giving off light. As we get further away from the candle and its radius grows, the surface area of where the photons are going to go, that grows actually larger and larger. In fact, it grows at a higher rate than a linear fashion. It's actually closer to an exponential or quadratic fashion, the amount of space that is spread apart on that energy. So that's something we have to consider. That's why the light doesn't travel as far. More things nearby absorb those photons and emit less of them, and there's even less bounced light overall, as well as direct light. So this is something we have to consider. That's why if you use the equations that we just prior talked about for a candle, then that candle will light everything at any distance, which is pretty unrealistic, right? We can't, for instance, take our flashlight and aim it at the top of the mountain, and then suddenly we light up the top of the mountain because there's no fall off of energy. So we need to be able to deal with that and represent that. All right. Yeah, because remember, even in air, the photons will interact potentially with the air there, and that's why you see games sometimes they'll have special effects where you have it's at night. I think Alan Wake is a good example, and the actual light lights up the fog and the mist in the air because it does interact with particles at any time. So we're not really talking about that right now, or ways to simulate that. But that's something you have to keep in mind whenever you're doing light, is the light is going to interact with any medium it passes through, and you always want to keep that in mind, how to simulate that. And there's some ways to do that. Okay, so we have two fall-offs here I want to talk about. It's a fall-off by radius. So this fall-off by radius really applies to both point lights, because they have a radius, and it also applies to spotlights, because spotlights too could have a radius. So that flashlight you turn on doesn't shine forever, and you might want that to fall off as well. So because a spotlight is just a point light cut off by a cone, you both can use this equation to apply attenuation, or to reduce the amount of energy the light gives off over a distance. All right, so let's look at this equation. Attenuation equals 1 minus clamp magnitude light position minus surface position divided by the light radius. So the light radius is what we're using to describe the absolute maximum distance of the light. Okay, so we're just kind of simulating that fall off by putting a hard limit on how far we're saying that our photons will travel before they're dissipated. Even though it's probably far more fluid than that in real life because of photons bouncing off of surfaces and air conditions and things like that. But for our purposes, to simplify things, this will make it a lot easier to calculate. So you can see here we have taking the magnitude of the light position minus the surface position. So what that means is if I have this this candle here, and let's say it has a fixed radius, let me choose another color here for this. So let's say this candle, we say, has a fixed radius that won't shine beyond. Then we have our surface position. Let's say we're lighting something on a table that's nearby. So here we have a table, and we have an object. My terrible apple here is being lit. So there's a point on this surface that has a normal and all that good stuff that we want to light using our point light equations for this candle. And what we can do is the light has a center point, and not only can you subtract these two vectors to find the direction from the light to the apple and vice versa, from this point on the apple to the light source, but this vector, before we normalize it, we can also find its length. We can find out how far that distance is. And that distance, let's say in this situation, is 9 units away. But let's say our radius is 10. So if we do a linear fall off, which is not really accurate to reality, but I'll tell you about a way to fix that here at the end. But if we just, for now, implement a linear fall off, the farther the light travels, it should fall off at the same rate. Like if the light is halfway away, then it should be half intensity. Then we can use this formula to figure out how much light should be reduced. How much light intensity should we reduce this by, rather than using the full amount that the formula dictates. So if that distance of that vector is 9, and that's the magnitude of returns, and we put it over the light radius, then we have 9 over 10, right? So we have 0.9, and then you say, well, is that like a ratio, a percentage? Yes, but would you think that 90% of the light should reach? No, that doesn't seem right, especially for a linear situation. It should actually be flipped, right? So if we're all the way close to the center, it should be 100% or 1.0, and all the way at the edge of the ring over at the radius should be 0%. So this should be closer to 0, not closer to 1. But because it's a ratio, we can just flip the ratio quite easily. Remember, ratio is, if we clamp it anyway, the ratio is going to go from 0 to 1. That's what this clamp operation here does. Just ensures that our our ratio, whatever ratio we calculate, is going to be between 0 and 1. So if we do that and we flip it by saying 1 minus the answer, our answer being 0.9, and you see it here in the formula, 1 minus, then we get the flipped ratio, or 0.1, which is 10%. So instead of saying 90% of the light should reach this point, we're saying, by flipping the ratio, we're saying 10% of the light should reach this point. And then you can simply take this attenuation factor and you can multiply it by your amount of light reaching the surface, and that's going to give you your reduction in energy based on distance. Okay, so a pretty easy thing to add to a spotlight or a point light. You just have to make sure that all of your lights have a defined radius. Okay, pretty straightforward. Okay, so you can use that for both spotlights and point lights. But this next type of attenuation is just for spotlights, this fall off from the cone edge. Okay. So what this is doing is this is going to allow you, in the equations we showed you for the spotlight, those equations, or those formulas would give you a very hard edge. But if you look at this light in the example, in this image, it seems to have a hardish edge, but it actually has a little bit of softness. So it's not actually using exactly this spotlight formula. If it was using exactly the spotlight formula, you'd see a much more hard, clearly defined edge along the spotlight. Let me use a different color here. Yeah, so along the edge of the spotlight, you would see a much harder edge, given this formula. But there is a way to soften it a bit, so you can actually soften it a little or a lot if you use attenuation. So, if you have a spotlight, like a flashlight, and you shine it, the edges of the flashlight aren't a hard fixed ring, right? They have some softness, they have some diffusion to them. So we want to be able to simulate that as well. And one way we can do that is by having more than one cone. The idea is we can have an outer cone and an inner cone. So besides having a regular cone, which we refer to as the outer cone, like this would be our outer cone. And remember, that's defined by our dot product value. We also want to have another dot product value. It's a little bit bigger. And when I say bigger, it's actually, remember, it's actually closer to the center if it's bigger, because if the dot product is 1, it's parallel, it's parallel, and if it's 0, it's perpendicular. So having a slightly smaller inner cone, slightly larger inner cone, means you actually have an inner cone that's a little bit narrower. And the idea here is now that we have 2 cones, we can say if something is inside the interior cone, it gets the full amount of light, minus whatever other, minus possibly this radius fall off. But now you have yet another potential to soften the cone edge. So if something is between the 2 cone edges, you want to soften it. And you can say if you're beyond the outer cone, then you get no light. If you're inside the inner cone, you would get the full light. And then you can have some linear drop, potentially. This equation I'm going to show you is how you do a linear drop between the inner and the outer cone. So really, this changes your light in such a way that instead of just having a cone ratio, you now need to have an inner cone ratio and an outer cone ratio. This outer cone ratio replaces your standard cone ratio. The inner cone ratio is going to be a dot product value that's slightly larger, which means it's slightly narrower. Okay, you just want to use a very small value because you were dealing in dot products, a small change like 0.1, 0.01, 0.5, 0.05, something like that, a small amount of change to have this cone not be this cone edge be soft. That being said, you could play with the size of the cone if you wanted a really soft, diffuse cone that really didn't have a hard edge at all. So that's the nice thing with this, is you can kind of play with it with the inner and outer cones. So if you look at it, it's pretty much the same as the left-hand side, the fall off by radius, but instead of using distances to the center of the light, we're going to use distances from the edges of the cone. And because the distances of the cone from the inner line of the spotlight are measured in terms of dot product, this is all done from dot product terms. So notice we're using the surface ratio, which if you remember our spotlight formula, the surface ratio is computing the dot product between the center cone direction and where the surface actually sits. So it's computing that right there. It's computing that dot amount. So by taking that value and comparing it and taking that difference, and then taking the difference between the inner and the outer cone, now we can create a ratio. Just like the light radius was the maximum value, the inner cone minus the outer cone is the maximum change in dot product that is along that edge. Now you might be saying, well, hold on. What about if you're inside the inner cone or outside the outer cone? Because this formula only appears to be if you're like in between the two cones. Well, the good news is if your surface with using this formula is inside the inner cone or outside the outer cone, we still have a clamp operation here. And remember, the clamp operation, if it's less than 0, it's just going to be 0. If it's greater than 1, it's just going to be 1. So we're just going to clamp this value between 0 and 1. So values that are inside the inner cone or greater than 1 are just going to be 1, and values outside the outer cone, which are less than 0, are just going to be 0. So this is going to work quite well in that regard. Once again, because we're doing this linear divide, we're going to get a ratio that's actually flipped from what we wanted. We want it to fade out to 0 on the edge, not fade in from the edge. So that's why you see that 1 minus there again, to flip that ratio around. So this is an effective way to have a nice soft outer cone for your spotlight source. By the way, notice the code we currently have in the spotlight to control the cone. It's this right here. And it's just a greater than, less than with a 1 or 0. So that's what makes the cone right now have a very hard edge. Essentially what you can do is you can take this equation here, this formula to compute the attenuation, and you can completely replace this code or this line right here. You can now get rid of that, because instead of having a on or off cone, we now have a smooth cone that's going to be clamped from 0 to 1, and that is going to make it actually a little bit nicer. You don't have a condition. There's no if statement in here anymore, so it's all just mathematics. So often if we can avoid any if statements in a shader, it's useful to do so. Oftentimes just doing the actual calculations or math for something is better than actually just doing a specific if statement and causing a branch within our code. So not always the case, but sometimes, but often can be the case. So yeah, if you want to do cone edge attenuation, just copy this and replace that line in the spotlight formula. Okay, so these are examples of light attenuation. So this is going to make it so your lights just don't go on forever. Which is going to be good because it's going to be a lot more realistic when you actually see them in a game scene or something like that. You don't want them traveling forever. Obviously, this does not apply to something like sunlight, because there's just so much energy coming from the sun, and the light source is so large. Is that energy going to fade out eventually in space? Yes. When it hits, or when it, is it going to be as much energy at a distance? No, but because it's also going to spread out. However, because it's so large compared to the Earth, there's no real value in calculating that minimal change in distance across the atmosphere, let's say. So just from this point of view, this can be very useful for kind of adding a little bit of realism to your point and your spotlights. I will say, though, that these calculations are, in fact, linear, yes. Because if you look at this candle here, and you notice as the radius gets larger, if we say double the radius, the surface area of that sphere of where the photons can go, that's actually not doubling in size. It's increasing at a much higher rate than that. So the fall off of light, the fall off of that energy, is not really a linear operation. It's closer to a quadratic operation. So and to make the curve, like I said, here's a linear curve, right? Or actually, I say this is fall off, right? So our light is falling off in a linear way according to this, but it's more realistic if it fell off much sharper than that. So light is going to fall off at a much sharper rate in real life than a linear fall off. The good news is it's very easy to kind of incorporate this into your lights, into your attenuation. Just multiply attenuation by itself and you're going to have a much more realistic fall off. Okay, so for instance, you have 0.5 is saying you're halfway through. If you take 0.5 and multiply 0.5 by itself, square it, then you're going to have 0.25. Right, so that's going to change the structure of your curve, and this means that the light will fall off much faster, and that's going to make more sense visually to do, and it's easy to implement. Okay, so just some things to keep in mind about linear light attenuation. Very useful things to add to your lighting shaders. All right, so last element we can add, of course, to our lights, of course, is the specular reflectance. All the things we've been showing you up till now, they have to do with like how do you calculate a light, where does the direction come from, and we use the dot product, right, along with the normal to compute the Lambertian reflectance of the surface. And we'll still do that, but all surfaces that are in, that you deal with also have a specular component, right? Some surfaces are shinier than others. Even surfaces that don't appear that shiny still have some reflectance in them if you look at them carefully. Even seemingly matte surfaces have some reflection in them. So it's much more realistic to have both a Lambertian component and a specular component to your lights. So this code right here, even though and we'll talk through it here in a second, but even though this looks pretty complicated here, it's really not too bad. And this is actually just a very simple, basic way to add a specular component. It's probably the simplest way that I know to do it, the fastest way I know to do it. You can get more accurate ways, but this is going to be pretty fairly cheap to add into your lighting equations and software. Okay. So as we talked about earlier, specular highlights, they represent this light that's been reflected, right, from a surface to your eye. So the idea is instead of being absorbed and then diffused and scattered and transmitted out that way and wavelengths absorbed, the light instead hits the microstructure, right, and then you see that in the form of reflected light. So you're actually seeing the light photons bounce directly off the surface instead of being absorbed and re-emitted and scattered. So depending also, the way the highlight looks is also going to be dependent on the roughness of the surface. Very, very, very smooth surface may have very sharp highlights, okay? Whereas a more Lambertian surface, or closer to a Lambertian surface, may have a very soft highlights that are much wider. Okay, if you can look around you and kind of observe that. So if you want your lights to have a much more realism to them, you're going to want to integrate a specular component to all your lights. And this is just something you add in addition to your Lambertian calculation. So this is something you do the calculation for like a point light or a directional light or a spotlight, and then you also incorporate this with that light using the same values that you have access to. So and per light, of course. So if we look at this, we have a view direction that we calculate, which is the world position of the camera. This is important. We have to know where the camera is in the world, which is pretty easy to figure out because you had to do the inverse on the camera anyway at one point. So you have the camera in its world space form. So you want to rip the position out of there and subtract it from the surface position. Okay. Or sorry, subtract the surface position from it. Surface position being, of course, where that point is that we're lighting. Now, the surface position, once again, when we're talking about these values, these are all in world space. Okay, we want to do all these calculations in the same space. You could do them in other spaces, but you would have to make sure every piece of data is guaranteed to be within that space. So just keep that in mind. When I'm showing you all these equations, we're talking about world space. So if we take the position of that in world space, we subtract it from the camera's position, we're going to get a vector that is from there to your camera. Okay. Now notice what happens. We're going to calculate this thing called the half vector. Okay. The half vector is called the half vector because it's halfway between the light's vector, or where the light is, as from the surface to the light, or whichever way the photons are coming from, and the view direction, which we just calculated. The view direction, of course, being the surface to our camera, surface right to us, the point from surface to us. And if we take those, and as you can see, there's a negative flip on the light direction here, so I'm going to draw these in different colors so it makes more sense. Okay. Let's use purple. So we're going to flip that light direction. We already have our surface direction, or from our surface to our camera. And we're going to compute this thing called the half vector, which is the vector that is halfway between those two vectors, which is easy to do. Just add them together and normalize them. And what that really does is that's just doing an average. Okay, that normalized call is just not only ensuring that this half vector that I'm drawing here is normal length, normalized, but it's halfway between those two vectors. All right. Now there is a true reflect calculation you can do that's out there. There are I don't want to say this is the way to do it. There are more accurate ways to do it for sure. And you should consider them when you have faster hardware and things like that, and faster shaders to use. But for now, this is a cheap approximation for adding specular highlights. So if we take this half vector here, what we can do is we can dot it with the actual normal of the surface. So you see the green normal here. If we dot that and this half vector, essentially, the closer the normal is to the half vector, the more bounced light we should see. That's the general idea of this. There's our half vector right there. Should have used a different color in the beginning. These are our other vectors. So we're going to dot these two. And the closer they are, the more bounced light there is. And that's essentially it. Now, if we left it just at that, and we didn't do anything else, we would, because of the nature of the dot product, we would have very, very soft, very diffused specular. So it would be like, might be okay for a very matte surface, something like that, or it actually might be too overwhelming for the surface of having that much of reflected light coming back, but it would be very diffused, and the points, the highlights would not be very sharp. So what we also have is the specular power term here. I'm circling that over here. That specular power, because remember, notice there's also a dot and a clamp of our dot product of our normal or half vector, we're going to get a value of the dot product. We're going to clamp it so it's between 0 and 1, and then the specular power, remember, is a number just raising it to power. Remember, this is a power, so we're raising it to something like the power of 2, or the power of 10, or the power of 50, or the power of 100. And when you raise a fraction to a power, if you remember in gamma we raised our fraction to 2.2 and actually caused the curve to lower. This is the same idea. We're by adding a higher specular power, we're actually reducing the area of where we're going to see the specular highlight. So that's going to sharpen, or going to make the areas, the popping highlights be brighter, or not necessarily be brighter, but it's going to limit them just to be closer to where those two vectors match up. And this is going to sharpen our highlights. And based on the microstructure of the surface, whether it's matte or completely smooth, you can play with this value to get it to be closer to the realistic appearance of what you see. Okay. Then you see there's a max command there, and that's just making sure that we don't go below 0 or what have you. So 0, we don't go underneath that value. Okay. And that's going to be our intensity. So how much specular intensity we have. Once we've computed our intensity, we can use it in the final calculation, multiply it by our light color. And there's another term called specular intensity. And this is just how, this doesn't control the shape of the highlight, this just controls how bright you want your highlights to be. Because remember, this is additional reflected light or bounced light that we are adding to our Lambertian term. So this is in addition to the normal diffused Lambertian term, okay? So this is, as you can see here, we have this purple teapot. The purple is coming from the Lambert, okay, the Lambert reflectance. And it's these white highlights that is coming from this specular component, this specular reflectance. So we want to combine them, we want to add them together. And the specular intensity is just a way to control the brightness of them, okay, how intense they are. But the specular power will control the shape, how diffused or how narrow they are, depending on the type of surface that you're working with. Okay, and once again, these are all these equations are based on observing light and things like that. So they're by no means are these accurate reflection or accurate physical models of what's happening, but they will produce in a fairly inexpensive way some good approximations. All right. So yeah, so you see this reflected light that's the final result. Remember, this is something you want to add to your Lambertian result. This is an additional light. So don't replace your Lambert term with this, add this to your Lambert term. And what that means, of course, is you're going to need a way to add these two colors together. So keep that in mind. You probably want to write a color add function or something like that, a combine function. Okay, so that is the specular component. It's actually not too bad to do. As you can see here, it's not that much extra code, and it really can help with the realism of surfaces. All right, so adding vertex lighting. Now we're going to talk about how do we actually implement these things that we've been talking about. So first thing I want to talk about is how to add it to your vertex shader, how to do lighting in your vertex shader. This is known as garage shading. Okay, so you hear the term garage shading. We're talking about performing our lighting in the vertex shader and then taking the final light results and then interpolating them to the pixels. So here's how you do this. So step one, you're going to add normals to your vertex structure and compute them. If it's a shape you made yourself, you're going to want to calculate them like we talked about earlier in this lesson today. Or you're going to want to load them alongside pre-built mesh data. So typically if you're loading a model or you have a model from a pre-made program like Maya or something like that, then it's going to come with normals. And those normals will generally be already normalized. but you might want to make sure that that is in fact the case, because you do want them to be normalized. All right, step 2, once you have your normals, once you have them added to your vertices, you're going to want to create lighting parameters, all right, accessible by your shaders. So just like you made matrices that your shaders could access, now you want to make lighting attributes. For instance, the directional light will likely have a color value of what color that light is, and then a normalized light direction, all right, in world space. It's important that you choose values that you know what space they're in. It's easiest to think about lights to exist in the world, so I recommend using world space values for that. So you're defining in world space what direction the light is shining. This is important to keep in mind, because the normals that you load in step 1, those are relative to the original triangles, which means they are going to be local. So you're going to have to adapt to that, because those are not completely, but those are two different spaces, right? Two different frames of reference. So if we're going to do proper calculations, they both need to be in the same frame of reference. Otherwise, our calculations don't really make any sense. So that's where step 3 comes in. So in the vertex shader, you're going to use the world space vertex information, which is the normal and the position. Remember, we have a matrix that can help us do this, the world matrix. It'll easily help us find the position of a vertex in world space. And we can also use it to transform the normal into world space as well. I'll mention a little bit more about that in the tips for lab. Okay. So once you do that, once you have all this information in world space, you can light this particular vertex using the formulas we've just discussed in this lesson. So once you've calculated the proper amount of light that should be reaching the vertex, you can store this information in the color attribute of the vertex. So essentially you're going to override whatever the color is, and it's likely you're probably not using the color right now anyway. You can override that color information with this light data, okay, with these lighting values, how much brightness reaches a particular piece of the surface, particular vertex. The final step is to simply let your colors interpolate like they probably are already. So that means that the intensity, the brightness of each surface as dictated by the light sources will be interpolated for every pixel in the pixel shader. Then you can simply take that brightness amount, whatever color that brightness might be, depending on the lights you have, the light sources you have, the reflectance models that you have, whatever it is that you use to decide that final intensity, and then you can multiply that with the surface color. That's called modulation. So that's basically taking your original surface color, and the surface color is then absorbing some of that light channels and then reflecting some of that back, so you see the final intensity. This way, by multiplying them together, you can't have, say, a green object suddenly appear to be Lambertian red, for example. They wouldn't reflect, it wouldn't scatter or diffuse any red light, though it might specularly reflect the red light. So that's something you got to be careful with, because that is added on top. But just for a simple Lambertian model, you would just modulate the two together. Okay. All right. Yeah, so that's pretty much it for garage shading. Okay, and this is the one you'll be doing in lab. You'll be doing garage shading. You may also see the term flat shading thrown around. This is an even simpler model than garage. What this is remember we talked about how you could have not only vertex normals, but you could have surface normals, which would be one normal per polygon. Flat shading is an even cheaper way to do light lighting, instead of calculating the lighting amounts per vertex and then interpolating the results, in flat shading, we just interpolate the light amount for a single triangle. We use that triangle's surface normal and figure out the amount of shading that that whole triangle has. Now that's going to produce a very faceted appearance. You're not going to get any smooth transitions because there's no interpolation at play, but it is very, very cheap to do. And you know, sometimes can come in handy if you want to do like a really retro type look where everything's really like faceted and looks very geometric. So that could come in handy for that. But yeah, garage shading or vertex lighting is what you'll be doing in the lab, because it's still pretty fast to do. Calculating this for every vertex is not too bad. With that said, that's not what you see in any game these days. Right? You're not going to see, maybe you might see it maybe on a very limited platform like an older smartphone or something like that. Maybe you might see a 3D game on an older smartphone might have vertex lighting because of the limited hardware and the performance. But on any modern console or PC game, you are going to see some take on Phong shading, okay, or per pixel lighting. So for a while now, we've been doing per pixel lighting because we've had the horsepower to do so. So this is essentially very similar to what we just did with a little bit of extra steps. All right. So it's the same as the last, it's the same as Gouraud for 1 and 2, right? Same as per vertex. You're going to embed your vertex data, make sure they're normalized, all that good stuff. But it gets a little different after that. Step 3, well, it's weird. I have 2 step 3s. I should probably change that. So, okay, so yeah, step 3, step 4, 5, and 6. Apologize for that. I should just write that in. This is 4. This is 5. This is 6. Okay. So step 3, you're going to add a world position variable to your vertex structure. So the idea here is you want to store permanently where your world position is. Because remember, during the vertex shader, your position is going to end up eventually in homogeneous projection space and then finally in NDC space for rasterization. But so in per pixel lighting, we do want to remember where the world position is for a little while longer than we would normally have it. Because the idea is we actually want to do our lighting in the pixel shader, and we're going to need that information. All right, so step 4 is instead of calculating the lighting amounts and actually doing our light equations per vertex in the vertex shader, we're going to move the vertex normal into world space. I mean, this is something we would do anyway in Gouraud. And we're going to save the information instead of using it directly. We're going to save it into the variable from step 3. So this is going to be our world position variable. We're also going to move the vertex normal into world space. Now you don't want to move the vertex normal into, and this applies for both Gouraud and Phong. You don't want to move it into projection space or NDC space, because the idea here is where we just use the normals for lighting, and since the lights are in world space, there's no reason the vertices shouldn't be in world space either. We're not rasterizing the normals. They're used to do this math. Okay. So step 5 is once you have that information calculated in the vertex shader, during rasterization, you're going to interpolate the new world normal and the world position components. All right. So instead of letting the colors be interpolated like we would in Gouraud, we're going to interpolate the position of the world vertex and the position of the world normal across the face of the triangle, like we would do for UVs or anything else. But this time we're going to do it for normals and position. Interpolation is wonderful as usual. It lets us do it, interpolate anything. So this time we're interpolating these mathematical components. The advantage to this is step 6, of course. And so in step 6, once you have these interpolated values, now you know the position in world space and the surface normal of every single pixel. And then that means you can individually light every single pixel using the equations we had discussed. are the formulas we had discussed. Now you're probably saying, well, isn't that like super expensive? Yes. At least in software, it's unbelievably expensive. Just think about how many more times your pixel shader runs than your vertex shader. With that said, it is far more accurate, okay? Because you are individually evaluating every single pixel and where it exists in world space versus guesstimating what that would be based on the vertices and how they interact with the light. So if you have a set of geometry which has very small triangles, then Gouraud might not be too bad. But for any large set of polygons that take up any decent amount of space that are large on the screen, then the interpolated results are just simply not going to be accurate. Think about a large set of two triangles on the ground. Imagine shining a spotlight at the center of those two large triangles. Well, in Gouraud, you wouldn't probably see anything because there's simply no vertices for the spotlight to touch. So there's really no calculations to be done, so that wouldn't work very well. But for Phong, since we're interpolating all those different data points and then lighting them individually, we would see very accurate results for how the light strikes each and every pixel. So keep that in mind. That's what almost any game you're going to play these days, it's going to be doing per pixel operations. So that's referred to as Phong shading, or sometimes blend Phong. All right. Finally, this is not really something we're going to cover in detail. I just want you to be aware of it. You're going to see games touting that they are PBR capable, or they have a PBR workflow, or PBR shaders. So PBR stands for physically based rendering. All right, and unlike these prior formulas that we've been discussing, that are more based on casual observation and trying to get a closeness there, these are just a bit more accurate, right? So they're taking less leeway with, they're of course still nowhere near perfect simulations. We don't have the performance anywhere near that to actually simulate the photons. But these are more accurate. They take more steps to more closely mimic the behaviors of not only the light on the surface, and they do things like energy conservation. They try to respect the fact that a surface material cannot give off more light than it receives. They try to be a lot more accurate in those terms, and they all actually respect the type of material, dielectrics versus metals. Dielectrics being things like wood or non-conductive materials versus metals that are conductive. They're going to interact with the photons differently, and these shaders are going to try to respect that. So there's a really good set of information here if you click on that source if you want to learn more about PBR. So you're going to see a lot of games, like the most recent in 2016, the most recent let's see, Far Cry. I'm sure Far Cry will have it if they don't already. What's it called? Yes, Nathan Drake. I can never remember the name title, but you probably know exactly what I'm talking. A Naughty Dog game. So it slips my mind right now. But anyway, they're doing PBR. A lot of these high-end AAA studios are embracing PBR rendering because we have more and more mathematical capability per pixel now than we did before. So it's okay if we spend more time doing more advanced calculations. So they're going to do more accurate simulations like torrents. These are still doable in real time with modern hardware, but they are a lot more involved. There's a lot more calculations that need to take place. But the huge advantage is that the surfaces, we don't kind of have to hack the numbers. We don't have to kind of like play with the specular component or anything like that, because because they're based more on real materials and metals, we can do things like look up tables for color values, or how they interact with light. and kind of have like prefab values, like a metal is different than an apple or something like that. So they're going to react differently to lights under a variety of different conditions. So this is really the way we're going to see this a lot in the future. This is the way forward. It's already common in quite a few games, and you're just going to see it become more and more of a standard. Already, engines like Unity and Unreal support PBR workflows, which honestly aren't that majorly different than older workflows. But they are doing a lot more calculations per pixel than what we had just covered. But like I said, it could be a whole lecture or more in and of itself to discuss physically based rendering. But if you're curious about it, here's a link to it, and it's definitely you're going to be seeing it quite a lot. Okay. So some tips for lab. Multiple light sources are going to combine with one another. This is important, that when two lights strike a surface, you don't multiply the results together, right? Because if one of the lights is really far away, then it's going to somehow dim the light that's close to it. So you don't want to multiply in that situation. You want to add. You add multiple lights together. That's important. So you're going to want a function that can add colors together. All right, so that's going to be important, so I would definitely write one. Also, make sure when you do add the colors together, not to overflow your color channels. Cap them at 255. That's important, because if you let them overflow, then suddenly your lights will flip over. Another light hits the surface, and suddenly the surface goes dark. You don't want to see that. So that's an important thing. Also, there's another reason besides lighting why you might want to add multiple lights together. And that is for something called additive blending. Additive blending is very handy for things like fire and things like that, where you have multiple bright surfaces covering each other, and then they get brighter toward the center, closer to white. So additive blending is also good for that. Okay. As it says here, the dot product can yield negative results when two vectors face away from each other, so you're going to want to clamp them, okay, between 0 and 1. That way you can use the ratios accurately. You don't have to worry about lights subtracting from each other, because you don't want that to happen. You might hear us refer to the term of clamping them between 0 and 1 as saturating them, because this is the function that's commonly used in hardware APIs like HLSL or what have you. Or sorry, hardware shading languages like HLSL to clamp values between 0 and 1. So that's where if you hear that term saturate, we're talking about clamping things between 0 and 1. If you want to make your life a little easier when it comes time to doing all these lighting calculations in your vertex shader or shaders in general, I recommend embedding your light attributes into a vertex, the global vertices, like you have your other attributes. Like for instance, you have like SV world matrix. I recommend you make a vertex like SV light directional light, or SV point light, or SV spotlight, or what have you. The reason I recommend that you do this is not only does the vertex generally have all the information that a light would have, like potentially it has a position, it has a color, it has a direction, aka the normal. It has a lot of the same things, so you can probably embed lighting information into your vertices. Well, at least most of them. Maybe a spotlight might need a couple more attributes, like cone, direction, and what have you. But you might be able to sneak those into a couple floats that are unused. So the reason I recommend this is you probably already have functions to do things to vertices, like to move them into a different space, or to do a dot product, or to do a cross product, or what have you. So being able to reuse those functions could come in handy. So rather than you having to math everything out by hand, here's an opportunity that maybe you can reuse some of your code. You don't have to do this, but I think it might make your life a little easier if you structure your code in a way to deal with vertices in a more flexible way. Something to consider. All right. Last thing I want to mention is a vertex has a normal. That normal is normally in local space. If you're going to do your lighting calculations, you're going to want that normal to be in world space. You have a world matrix designed to take your positional data and move it from local space to world space. You can also use this matrix to move your normals into world space. The thing I want to caution you though on is a normal is not a homogeneous coordinate, okay? It's just a normal 3D coordinate, x, y, z, no w, all right? Because we're not doing things like perspective on our normals. Not only that, but our normals, are directions. We wouldn't want to translate them anyway. You wouldn't want them to be moved. So really you just want to rotate and possibly scale, but mainly just rotate your normals into a new space because they are just directions. So you can do this if you just multiply your normals by the 3x3 portion of your world matrix. That being said, if you do that, you might have to write some new code to do that. Another way you can do that potentially is you could temporarily add a W component, but it's very important that that W component for your normal not affect the normal for movement. So if you normally multiply a vector 4 with a matrix 4, it's going to use the 4th row and the 4th column. You're actually trying to avoid those last two, right? You don't want them to affect your normal. You just want to rotate it. So to do that, you can set the W to 0, and that will essentially eliminate the 4th row and the 4th column. All right, so that's a handy thing that you can do to reuse some code. That being said, you probably already have a 3x3 operator, so that's only necessary if you choose to reuse your 4x4 operator. But keep that in mind. Don't go translating your normals. They're not meant to be translated, just rotated. All right. So there's your final recommended reading assignment. I know this last video was quite long, almost an hour here. But, these last details of how to actually incorporate this is important. I do recommend you read this chapter 26. Kind of helps bring everything together, what you've learned in this course, and how you can bring that into a kind of production environment, how it all gets used. Very interesting chapter. Recommend you look over that. And also, don't forget to study for that final. That's coming up. So you should get a study guide, I believe, for today's lab, alongside today's lab. So make sure you look over that carefully as well.